Welcome to Lesson 8D, Reflecting Shock Analysis. In this lesson, we'll discuss what happens when the shock reaches the end of the shock tube, and I'll go through the analysis to calculate shock speed and shock Mach number for a reflected shock. And I'll continue the example from the previous lesson, including a reflected shock. First, consider an open-ended shock tube. Here's our shock tube, our moving contact surface, and the shock moving supersonically at speed vs down the tube. For this case, suppose the shock tube is just open to the atmosphere. So back pressure is atmospheric pressure outside the shock tube. And P1 is also atmospheric pressure since this is all open. Recall that this is region 1 and region 2 is behind the shock with speed V2, which is the same as the speed of the contact surface. Let's consider the case where this shock is strong enough that the flow here is supersonic. And let's look at what happens at the exit. Right after this shock exits, I'll ask the students, is this overexpanded or underexpanded?
I'd say it's underexpanded.
That's right, Sean. And how did you know that?
Well, to be honest, I just guessed.
Okay, thanks for being honest. It turns out that it's underexpanded. Let's think about this. Again, PB is P atmospheric, and that's also equal to P1, where 1 is the location before the shock. But P2 is greater than P1 since we crossed the shock. So the gas coming out here has a higher pressure than the back pressure. And if you recall, we called that underexpanded. The jet will flare out something like this, as we've discussed previously, and the shock itself will eventually morph into a spherical shock that expands outward. Here's a picture of this. You can see a little bit of flare out here, and then the shock has formed into a spherical shock. I also have a short video clip from the PSU Gas Dynamics lab. Now consider a closed-ended shock tube. Suppose the end of the shock tube is a wall. Again, we have our contact surface and our moving normal shock with regions 1 and 2, and this is at some time T1, and X is 0 at the initial location of the diaphragm, where it burst at T equal T0. So we can come down vertically from these locations and sketch our XT diagram. At T equals 0, the shock starts and moves along like this until it hits this wall. This time T1 with the shock here is here. And recall this is region 1, region 2, and region 3. And let's not worry about the expansion fan for now. As this shock moves along, it hits the wall, and what happens is it reflects. Let's call this speed VSR. For shock reflected, this will be the speed of the reflected shock. This is still region 2, but since we've already used regions 1 through 4, let's call this region 5. Now consider a fluid particle at this location, which on the XT diagram is stationary until the shock hits it. Then it has to move parallel to VCS until it hits the reflected shock, since V2 is VCS, as previously. But then it hits the reflected shock. Then what happens? Well, the key is that since this is a solid wall, V5 must equal 0. In other words, the gas is now stationary again, so the fluid particle on the XT diagram is again vertical. In other words, 0 speed, just like it was 0 in region 1. Let's pick some later time T2 after the shock has reflected, and again sketch our shock tube. The contact surface has moved here at time T2, and the reflected shock is now here, moving at some speed VSR. And this is now region 5, which has reflected off this solid wall. So I'll remove this portion of this shock tube. This is region 2, and this reflected shock moves at some Mach number MSR, the Mach number of the reflected shock. So now we need to analyze this moving shock, moving from right to left now, from region 5 into region 2. In the moving shock frame of reference, the shock is moving from region 5 into region 2 at speed VSR in Mach number MSR, where we know that V5 is 0, but region 2 is still unaware that this shock is coming. In other words, V2 is still equal to the speed of the contact surface. Note that we're used to calling the region in front of the shock 1 and the region behind the shock 2, but now we have to consider 1 as 2 and 2 as 5, and we can call this VAS as well, or region AS, after the shock. Now we have to transform from the moving shock frame of reference to the stationary shock frame of reference. Here's our shock with regions 2 and 5, but now the shock is stationary. And how do we do this transformation? Well, since the shock is moving to the left, we have to add the shock speed of the reflecting shock, VSR. And from the stationary shock point of view, let's call this speed V before and this speed V after. So V before is equal to VCS, speed up here, plus VSR, where we've added this speed to do our transformation. And I'll draw this longer since we're adding VCS and VSR. This is a high speed. Similarly, V after is V5 or VAS aftershock plus VSR. But VAS is 0, as we've pointed out here. So V after is simply VSR. Now we can analyze this like we did before for any stationary shock. For example, conservation of mass in this stationary shock frame of reference is rho before, V before, equal rho after, V after, from which we can write rho after over rho before is V before over V after, and from these two equations, this is VSR plus VCS over VSR. And we also know that MSR, the Mach number, is B before the shock over A, speed of sound, before the shock. Again, using this equation for V before, this is VSR plus VCS over square root of gamma 1, R1, T before, which is the same as what we had called T2, which is known. So this denominator is known and VCS is known, but we need to find VSR and MSR. Well, we have these two equations, but we need an expression for this ratio of densities to MSR in order to be able to solve this problem. So let's use our shock equations. Recall for a shock from 1 to 2, rho 2 over rho 1 is V1 over V2 is gamma 1 plus 1, M1 squared, over 2 plus gamma 1 minus 1, M1 squared. But here, our Mach number MSR is our old M1 in this equation. So this equation becomes V before over V after equal gamma 1 plus 1, MSR squared over 2 plus gamma 1 minus 1, MSR squared. And from up here, this is equal to VSR plus VCS over VSR. Let's call this equation 1 and this equation 2. We know everything here except MSR and VSR, where we're ignoring this part of the equation. So with two equations and two unknowns, we should be able to solve for VSR and MSR. Let's consider our example shock tube problem from the previous lesson. We had calculated VCS A2, and we know that gamma 1 is 1.40 since gas 1 was air. So we just iterate 1 and 2 until convergence. My result is MSR is 1.675 and VSR is 340.3 meters per second. These are our final results after some iteration. Some comments. This set of equations is what mathematicians call stiff. In other words, it's difficult to converge. I used an under-relaxation technique to get it to work. Notice that MSR is less than the original MS, which I'll write up here from our previous analysis. MS was 1.8926. And note that VSR is the reflected shock speed moving to the left. I also note that it is possible to generate an equation for MSR as a function of the original MS and gamma 1. This involves lots of algebra, which I won't go into, but if anyone's interested, see the book by John Anderson, Modern Compressible Flow with Historical Perspective. I'll write out his equation here. And since we know gamma 1, this is a relationship between MSR and MS. And we know MS from our previous calculations, so we can solve this for MSR. We get MSR is 1.675, which agrees with this, which makes us happy. What about other properties in region 5? Well, again, we'll use our stationary shock frame of reference, where we have M2 and then across the shock M5, but our shock equations are in terms of region 1 and region 2, so we have to be very careful with our subscripts, where we have our old 1 and our old 2 being now 2 and 5. So for example, we can calculate T5, the temperature, as the ratio T5 over T2 times T2, where T2 is known, from our old shock equations for T2 over T1, which is now T5 over T2. So watching our subscripts and using gamma 1, we have this expression for T5 over T2, and noting that this M2 is equal to our reflected shock Mach number MSR. And I want to write this more carefully as a 5, not an S, where we have the intermediate step of calculating M5 from our previous shock equations, which we can plug into this equation. The results are M5 equal to 0.64717. T5 over T2 turns out to be 1.4404. And since we know T2, we use this equation to get T5 equals 688.03 K. Notice that this is very hot. In fact, one of the uses of shock tubes, since they generate a very high temperature, is to study gas ionization. The shock hits the end of the shock tube and reflects, and if the shock is strong enough and the temperature is high enough, you can ionize the gas. Similarly, we can calculate P5, rho 5, etc. as needed. We find that P5 is also very large, in other words, greater than P2. Just like T5 is greater than T2. So we also get a very large pressure rise after the reflected shock. Finally, I'll show a short animation created by NIST that shows a shock tube. This shock tube has 3 pressure sensors, and you can see the diaphragm. When it breaks, you get a shock traveling down the tube. When the shock hits the end of the shock tube, it reflects. The pressure rises as soon as the shock passes one of the sensors, and when the reflected shock passes the other way, the pressure increases again. In the next lesson, we'll look at the other side of the shock tube, where the expansion fan reflects off of the wall. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.